Ladies and gentlemen, it is Friday and 3 p.m., only 2 hours away from the weekend. Welcome everyone to the first Epic Quantum online technology meeting. What a special day. Some predict that by 2050, the global market of quantum technologies will be worth 300 billion euros. Frankly, we don't need to wait that long. With great companies like QuiX, Quandela or Keysight already launching first generation products, tomorrow will arrive sooner than you think. Remember this? The most romantic thing in physics is when two particles are entangled, or as I call it, dancing to the same music. And no matter how far away they are from each other, any interaction on one of the particles will have an effect on the other. They will dance and spin in opposite directions. You see, I'm still in love with quantum. Epic is launching 6 deep dive discussions on quantum photonics. We start on Friday the 12th of February to examine pathways for accelerating qubit generation. It is at the heart of the race for commercially viable quantum computers. We will focus on photonic solutions for qubit generation and quantum data processing. We will bring together companies developing photonic integrated circuits, single-photon sources, and single-photon detectors. Our discussion will explore state-of-the-art quantum information processing technologies, as well as comparing photonics qubit generation with competing technologies like trapped ions or superconductors. So join us on Friday, February 12th, 2021 for a top-level discussion on quantum technologies. Be part of the quantum photonics revolution. It is such a special day for us because both Sana and me, we have studied quantum physics and we really see now the merging of the photonic industry with all the quantum hype, but also all the quantum push that we are having these days. And we thought 2021, after this year 2020, 2021 is the year that Epic also incorporates quantum technologies. And the person who's going to lead this adventure is Dr. Sana Pyka. Dr. Pyka, thank you so much for this. How do you feel? How do you feel about leading the quantum business of Epic?
I'm so excited about this meeting. For a start, I'm so happy with all the guests we have here, leaders of the market. And we are going and we're giving a push to the industrialization of quantum technologies. It's going to be off the shelf soon.
So if you have any question, go to Sana, and she loves talking about quantum technologies. Epic is now 687 members. We are only 13 members away from me having to put a new sticker over here. We are going to have soon 700 members. Who will be the member 700? I have no idea, but I hope at least a very cool, innovative startups. I love startups. I also would like to say that I'm talking today on behalf of a fantastic team of people, 15 people, 7 of them with PhDs, most of them women. Yesterday was the day of women in STEM, so we celebrated very, very well with our fantastic team. We organize events, we provide access to the network, we help companies raise capital, and we never get a cent because all we do is connect people. And we have the biggest website to find a job in photonics, jobsinphotonics.com, and all of you know this because you're an Epic member. Because you're an Epic member, you also have access to a long list of market reports from Thematis, from Jörn, from Strategies Unlimited, well, you name it. But today I want to talk only about quantum. Today is Friday, 3 p.m., only quantum allowed. Today we are launching this quantum initiative at Epic. It's a big day for us. We start with bringing our friends together, and now we are going to expand this to the defense, to the medical, to the e-mobility, to the quantum communications, and we'll finish again bringing all of us together with those end users scouted along the way to see what kind of business we can do. Today we have to, of course, acknowledge that this event wouldn't be possible without the support of our fantastic sponsors from Switzerland, Ligentec, silicon nitride foundry services. So you need silicon nitride manufacturing. These people in Ligentec in Switzerland, they managed to do the whole manufacturing process, achieving world record low losses. And you're looking for a partner in quantum research, all the way from Delft in the Netherlands, QuTech. QuTech is one of the worldwide leaders on quantum research, but what makes them special, this is a collaboration between TU Delft and TNO, and they focus on really bringing world-class science into the real-time and real-life applications, thanks to the cooperation with TNO. QuTech, thank you so much for being a member of Epic. Thank you both for sponsoring this fantastic first quantum meeting. Sana, what's going to happen over the next 2 hours?
You will hear what is the top market development in terms of photonic quantum computers for a start, and quantum computers in general. We will hear from Orca Computing, IBM, QuiX, Photonic ILT, Fraunhofer ILT, Keysight, and Xanadu. And if you look at the supply chain, you will see that we gathered for you today the key players in this field. We have the quantum computing solutions, of course, with IBM, Microsoft in the room. We have the quantum computing platforms, and we will hear from the R&D side. We will hear from the market side. We will hear from the photonic integrators. It will be an amazing meeting today, but please notice that all of the companies you see here on this slide are the people who registered for this meeting. At Epping, we have the largest network of quantum companies and startups. So let's hear from them.
Indeed, Sana, as you said very well, this slide only corresponds to the people who registered for the meeting today. So you're an Epping member and you miss your logo here. That only means you did not register. Please make sure that you register for the upcoming meetings. All you have to go is to go to our website and go there, epic-asoc.com. This meeting is live broadcasted in YouTube. So hello, YouTubers of the world. If you want to get in touch with any of the participants today, send me an email, jose.pozo@epic-asoc.com, and I'll make the introduction. Do not forget to post any question that you have in the chat and we'll read into the room. But this is also, of course, valid for the people in the Zoom room. We have a private chat. Please use it to have your internal private discussions with the other participants and do business, because this is what it's all about. And if after the meeting you want to get in touch with any of the participants and you didn't have a chance to talk to them, send me an email, jose.pozo@epic-asoc.com, and then we'll make the introduction. So Sana, what do you say? Let's start. Let's start. Richard Murray from Orca Computing. We had a fantastic call last week, and Richard says, we are really gonna do what other companies are doing in quantum computing platform with integrated photonics, companies like PsiQuantum, like QuiX. We actually were thinking of doing everything with optical fibers and off-the-shelf components, and only do the material research when it's needed. And I think that's mentality is something that we cannot fit better in the Epic community. I want Richard to share this vision with everyone, and most important, to tell us how we can help Orca Computing be even better than it already is going to be. The floor and the attention of everyone goes to Richard Murray, goes to Orca Computing.
Wow, thanks, Jose. What a great introduction. Let me just share a few slides quickly on things that we're doing. So, hey everyone, nice to meet you all. Fantastic. Thank you so much for Epic for organizing this great meeting in front of so many photonics, leading photonics companies. So my name's Richard Murray.
Richard, can we go presentation mode? I want to see big. I want everybody to be impressed by this.
There we go.
Perfect.
So there's our nice picture. So nice to meet you all. I'm Richard Murray, CEO and co-founder of Orca Computing. And we're, like Jose really nicely said, we're looking to approach quantum computing, photonic quantum computing, from a new and fresh perspective. So a slightly different way that incorporates one of our novel proprietary technologies, quantum memory, so the ability to store and retrieve single photons, and also leveraging optical fiber and telecoms equipment. And we hope, as well as addressing the sort of hard technical challenge of scaling a quantum computer, if you can try and make these systems work with non-bespoke components and telecoms, lasers and things like this, that aids your journey to market and makes your business a lot more flexible. So there's a large sort of technical drive for the company and the mission, and also quite a large commercial side. So quite a lot of commercial thinking behind what we're doing. I guess as I was the first speaker, I thought I'd flash up this slide, slightly tongue-in-cheek, because some people, say McKinsey, have published a report saying quantum computing is going to be a $1 trillion market by 2030. I say that slightly tongue-in-cheek because I think that does display the sort of optimism, the huge potential around quantum computing. Whether it actually becomes $1 trillion, $1 trillion is a lot of money. So I think it's going to be massively disruptive and massively important to the computing market. I wouldn't personally say it's going to be $1 trillion by 2030, but I think it's going to be big. And my reasons for thinking that are actually quite grounded. So the more you look into high performance computing, the more you do find that it struggles. It struggles to scale up to help solve artificial intelligence problems, machine learning. These are all sort of things that we've all heard about, but actually are constrained by the scale of current classical computing systems. And this audience probably knows that industry is moving towards photonics. Photonics interconnects are more and more important and driving down latencies and things. Quantum represents the next level up for the high performance computing industry. So helps it sort of address some of these really challenging and important problems for society. So I'm sure everyone else in the panel today would say that. So as I was the first, I thought I'd get that out of the way. And if you're trying to do quantum computing, there are a number of different approaches, and other people on the panel are representing those other approaches. There are other approaches that are doing really well, but photonics does present a really interesting possibility of a way to do quantum computing, which potentially is highly scalable. And the reason for thinking that is obviously quantum information is fragile, it's easy to decay. And so therefore, if you imprint your quantum information into something like a photon, and if you make the bit dependent on whether your photon is in one optical fiber or another one, something called rail encoding, it's quite hard for that information to change. That's pretty hard. So your resilience to errors, so the chance that a photon will skip from one optical fiber to another one is obviously quite rare. So it's quite a robust platform, and also potentially offers you some nice advantages like room temperature operation, like long coherence times, and then this nice idea about high connectivity. So in the quantum computing space, numbers of qubits is one thing, and that's an important parameter, but companies like IBM, who've been sort of developing the quantum volume scheme, know that the amount of connectivity, the amount of entanglement you can create between qubits also is a powerful indicator of the performance, the usefulness of a quantum computer. So photonics highly connective and therefore highly scalable. And there's not a lot of sort of difficult manufacturing involved in photonic processors. So our qubits aren't determined by sort of how you can manufacture a circuit or the quality of which you can manufacture a circuit. So therefore, it presents some interesting opportunities for photonic quantum computing. The last point there is just about our nod to sort of other degrees of freedom for photonics. And one particularly really exciting part of photonic quantum computing is you can encode information in your qubit, in your photon, in a number of different ways. It can be spatially encoded, whether it's one optical fiber or another one, temporally encoded, so which time bin your photon is contained within, and then obviously for this audience will understand, spectrally encoded, so either frequency or spectral mode multiplexing. So these are all additional elements, additional degrees of freedom that can vastly improve your information density that you're able to carry within a qubit. So photonics is really exciting. The one huge challenge that I think everyone here in the quantum computing space would recognize is the challenge. And the challenge is essentially that photons are resilient to noise, but they also don't like interacting with each other very much. So you take two photons, you want to create some entanglement between them. That can happen, and there's a sort of process of interferometers that allow you to do that. But the whole result of that is probabilistic. It's only got a certain chance of being successful. So therefore, if you want to build up a very large entangled state, so lots of photons all entangled, you're multiplying together several stages that are sort of have only a certain chance of being successful. So there's a so-called sort of scaling challenge involving the more you scale the system up, the less likely it is that all of your operations are going to be successful. So it scales quite badly. Moving on to Orca, Orca's unique approach is to focus on using quantum memories. So the quantum memory is a sort of small vapor cell, and we can do sort of 2 photon absorption within that cell. And the upside is that you're able to store and retrieve photons, single photons, on demand with very, very low noise floor, so while preserving your quantum information in those single photons. So we were looking at that for quantum key distribution, quantum communications. The lifetime is too short to act as a sort of repeater for anyone in the audience interested in that. But it still remains as a really important and interesting component for more local networks, so for use in photonic quantum computers. So our architecture relies on optical fiber, but it also relies on using these memories to overcome this, what's known as the redundancy problem in quantum optics. I'm moving through this quickly because I think I've only got so long to speak. And what's quite unique about Orca, which we're particularly focused on now, hopefully to describe the potential for photonics as a really interesting platform, is something we call time domain quantum computing. which is where rather than lots of separate optical fibers, lots of separate spatial modes, you flip things on its head and you contain, you have one optical fiber element with multiple photons. And what you can do is manipulate that system to create some degree of entanglement between time bins, so within the time domain. And okay, this is a sort of a separate project we have in the company to hopefully try and explore what we call resource efficient quantum computing. So move away from needing lots of sources, lots of detectors, and in the sort of grand scheme of things, we are talking about millions of components, to potentially, and I would say this is sort of something we're exploring, but potentially something which is much more resource efficient. So potentially just using a smaller number of sources and smaller number of detectors. And obviously, if we can do that, then the business advantages are quite clear, and allowing the system to scale well. So that's me. I hope that's sort of a good introduction. Obviously, just a whistle stop, but I'm happy to answer any more questions if you have them.
Thank you so much. It was a wonderful talk. It's very good that you mentioned market report, because Epic offers market reports to the Epic members. We have one on quantum technologies from Jörn. So please contact Jose if you want to know more about that. But regarding your talk, it's very nice to know what you're doing, but let me know the challenges, or what can the others do for you? What are the main challenges for you?
Really, really good question. The huge challenge for any type of photonic quantum computer, actually excluding Xanadu, I'll let them introduce their own platform. For us, it's loss. So we start off with lots of single photons, and we need to so one element is a deterministic single photon source, so a way of producing very high quality, indistinguishable single photons. But then after that, everything is about being able to perform operations, so switching, multiplexing, and detection, while maintaining as many of your single photons as you can. So we talk to people about wanting sort of losses of less than 1 dB, so very fast switches at less than 1 dB. So very, very strict requirements about each photon represents one bit of information. So those cute photons need to survive to the detection at the other end. So in a nutshell, loss is the biggest challenge for photonic quantum computing. But then everything else, yeah.
Yeah, I will get back on that. I will let that sink a little, because I would like to introduce you to one of our members that are very famous in producing single photon source, Quandela. But before that, I have a question for you from CSEM. Amir, would you like to ask the question?
Yes, actually, so I was very intrigued about your actual quantum memory is something I actually personally work on this in my PhD. I was wondering, can you tell us about the T1, T2 times of your quantum memory? What is the time scales we are talking about here?
Well, I will be honest in saying we are talking about very short lifetimes. So the information stored within thermal rubidium vapor. So your lifetime's limited by the amount of time that your vapor stays within the sort of the beam waste of your light field. So you are talking about a few hundred nanoseconds, say 500 nanoseconds. So if you imagine our game is to try and do as much of the processing, so increase the clock speed on our laser systems, the rep rate of the single photons as high as possible, so you can get multiple photons within that 500 nanoseconds. And
obviously, what is your gating time? What is your gating time? What is your gating time?
Well, for photonic, it's very high. It's related to the speed of your detectors, so you can perform many operations within that period of time.
May I ask about the connectivity part? So you're essentially providing a connectivity service, and your claim is about the off-the-shelf components, right? So that's the sort of a key advantage there as well. You don't have to develop a proprietary technology. What are the size limitations there, and how actually that would scale? And I want to have a relationship with the scalability and the cost element of that kind of a solution compared to a more sort of a proprietary technology, which can be pretty well controlled in size limitations.
Really, really good question. So obviously, in the long time scale, you are talking about very high numbers of components, so millions of components, maybe for sort of full fault-tolerant operation. There is a little bit of discussion in the community about how useful smaller scale systems are. So if you're familiar with there's these things called NISQ quantum computers, so noisy intermediate scale quantum computers, sort of hundreds of qubits, and how useful those can be. the jury's out about how useful those systems are. So I would say I'm honestly a little bit skeptical about the use of the word manufacturing. So a lot of people at this point say the only solution is integrated systems, integrated photonics or otherwise, because when you have modular components, there's no way that you could possibly scale up to large numbers of components. So I guess at that point, obviously I'm selling one approach. I would sort of say two things happen. One, integrated photonic systems are hard for quantum. So the sort of loss element isn't naturally easy to solve when you're trying to run a quantum system over integrated photonics. So I wouldn't necessarily say that very miniature sort of chip scale components are necessarily the way forward as sort of as attractive as it is to be able to leverage that existing platform. And I guess the second thing is our systems, if you are talking about modular components, you can still make modular components quite small. And if you imagine a quantum system to being a sort of few racks of electronics, so long as, I won't argue that as long as we can get our memory elements and things like that down to be quite small, I think it's not necessarily going to stop people wanting to use quantum computers in the sort of near to long term. So and this is obviously a little bit of a rant. My own rant is not to ignore things that aren't integrated or chip-based quantum solutions, because there is a bit of flexibility for people to want to use systems that are slightly larger that work. So I think that's the main challenge, not necessarily whether you can make them work and work small. I don't want to I think it's important not to confuse those two different things, if that makes sense.
This is why it's very important to have companies like Sony in the room to push the scalability directly. They don't think much.
We have looked into it, and I think one of the reasons I'm very interested in listening from Xanadu and other counterparts as well is that there are so many domains, whether you look at the superconducting QCs or photonic or trapped-ion neutral atoms, diamond, and the war is about the scalability problem, right? So if you're going towards these fault-tolerant systems, and some claim to the need for about 1 million qubits as well, the scalability of the practical equipment is going to scale with it, which is going to directly involve the costs associated with it. Somebody will have to pay for it eventually. So how are you going to retain that? Because there has to be a limitation there for the scalability.
I actually completely agree with you. I guess the only thing I would add is, in terms of scalability, there's the sort of size, practical element and cost element of things, but there is also just getting the thing to work at scale as well. And I think those are two important but separate considerations. So you don't want to make something that's really, really small but just doesn't work. And I'm not saying that integrated photonics won't work. It's really attractive and a great platform. I'm just saying there are others not present in this call who completely dismiss, say, our platform for discrete components because it's always going to be too big, which is something that I don't think is actually realistic. Although
I think another point would be how to get to that scale, that point, right? Where you can actually have like 1 million qubits in a small chip, but that's probably too far ahead. So the road to get there would require probably a lot of modular schemes as well. Then.
As much as I love to hear this conversation, I'm so curious to hear more, and I'm sure you will have a lot of happiness here and now from Valerian. Valerian, you are the pride of France in this field. Tell us about Quandela.
Can I introduce quickly Quandela?
Absolutely.
Right, 1 minute, right?
Yes, you can just share your slides.
Okay, thank you very much. I prepared a very few slides just if you want to know more about the.
They can reach out to you. Just give us the basic of your work, and they can reach out to you.
Exactly. Just to tell everyone who are we. So Quandela, we are a French company based in Paris-Saclay. Now the team is about 15% spin-off from CNRS Lab and Université Paris-Saclay. So just to give you some pictures, and basically our building block is a key for the development of quantum computers like the one developed by Orca, for example. We have a technology which is the widest sources of single and indistinguishable photons that is available on the market, actually. I'm very proud also to mention that we are a provider of focusing project, which is a European project, and I'm sure Jörn from QuiX will mention this and tell you more about the project. So, a brief idea of our product now, 2021. This is a lab in one product, actually, which includes lasers, electronics, and cryogeny which chamber, which inside there is a fiber single photon. And with this device, actually, it's going to be the first and bright plug-and-play single photon sources for quantum computing applications. So actually, this is the brightest source of optical qubits. So that's the idea. Thank you for giving me a few seconds and chance to present what we do here.
Of course, Valerian, it's very important, and your company came first when you speak about single photon sources. I hope we are still a lot of connections after this, but we cannot speak about quantum computers without having IBM in the room. I'm very happy to present our Najla Said, our next speaker from IBM. How are you doing, Najla?
Thank you. Hi everyone. I'm doing very fine. Thank you. Hope everyone can hear me well.
Yes, we can hear you
Perfect.
very nicely. Please start your presentation.
Thank you very much. Just a moment, I share my slides. Okay. Perfect. Hope everyone can see my screen. So good afternoon, everyone. My name is Najla Said. I am an IBM Quantum Ambassador. And I want to present very shortly our quantum computing technology, even if it's directly not related to the photonic part. As you probably know yet, we are working on superconducting qubit. In particular, we are, here you can see a picture of one of our processor in which you can see the quantum bit that is realized with the Josephson junction, And as you can see, we can control this kind of processor thanks to microwave resonator. And this is the reason why we are sticking to this technology, because we, so to say, are very good in working with this kind of connections. So with all the electronics that we use to control our computers, and moreover, we are convinced that we will be able to scale. In order to witness this kind of conviction, we created this comparison that is between the Moore's law for classical computing that you can see here on the left, while on the right you can see a plot of the growing through years from 2017 up to now of the quantum volume of our computing systems. So quantum volume is a kind of metric that we developed in order to explain the performance of a quantum system. This is not given only by the number of qubits, but this is also comes from the error correction, error control, and so on. So as you can see here, last year we have a big bounce because we were able in September to announce that we reached the 64 quantum volume on our Montreal system, and then in December we were able to reach on the very same system a quantum volume of 128 by just working on the software part. So again, at the end of last year, we announced our roadmap for the scaling of the quantum computer. As you can see here from this picture, we expect by 2023 to reach and go beyond the 1,000 qubits together in one processor, and then hope to continue well beyond on the path to the 1 million qubits processor. So how do we work in quantum computing, and how do we collaborate? We created an IBM quantum network. This is a network that really contains a lot of enterprises, academies that are willing to work on quantum computing with us. As you can see, we have more than quite 250,000 of users. We have up to now released up to 29 quantum computers, And some of these processors, you can find them online. It's very easy. You can just search for IBM Quantum Experience, and you will be directed to our webpage on which you can just sign in with your email and use some of our system, the processors that are publicly available. We really are working a lot in order to develop a network of enterprises and indeed researchers in order to grow this technology and try to get it always more applied to real world problems. So we are asking usually what can we do to create a quantum workforce? Well, we really believe in the open access, and that's why we take some of our processors open to the public so that everyone can use and learn how to work with the quantum computer. We are working on our software development kit that is open source, so you can find the code on GitHub. You can also contribute to the community by proposing changes, by proposing additional work. And in education, you can find a lot of education also on our IBM Quantum Experience website, and also by really cooperating really tightly with the universities and academies all over the world. So here is, I hope, okay, perfect.
Thank you very much for a great presentation. We couldn't do a quantum activity without the support of IBM. Epic member IBM, you've been supporting Epic already for many years, and it is so great to have you here as the company who's already done it and is gonna help the rest of the supply chain to be successful. This is an Epic meeting. You know what Epic is famous for? Cooperations. So I'm gonna ask you the Epic question. Is there any particular challenge, anything that you think the rest of the photonics community worldwide, 685 members, can help you with? What can you do for them? What can they do for you?
Okay, absolutely. So as I said before, we are really working hard on the software part and also on the software control of the hardware. You would find in our Qubit kit, so the software development kit, also a lot of modules that are there to control the pulse that we send to our processor. So we are really aiming for collaboration in this kind of activities, and we expect, I don't know, maybe someday this kind of processors will need to be connected to each other. So probably we will absolutely need photonics for this.
We have Richard from Orca Computing asking if photonics is part of your roadmap. I think more or less you answered that. What I want to also ask you is that you said that you have already over 300 contributors to the quiz kit. 300 contributors to the quiz kit. So I'm going to ask you for your Santa Claus Christmas list. What do you want that you don't already have?
Oh, yes, we are really open for collaboration. So if you have any suggestion, as I said, we are very focused now on error correction, but if you have any suggestion also on application, on contribution, just feel free to reach to me and I will try to send you to the nearest quantum ambassador in the world.
Najla, stay tuned because I'm going to come back to you in a few minutes. But now I want to have a really super nice discussion. In the first presentation, Orca Computing said that they are looking for, well, actually the question is better if it comes directly from Jeff. Jeff, one of the investors in the room, you have something in your mind, right?
Yes, on Richard's presentation, and the foundation of their work is use commercial parts where you can, research where you need to. And in the presentation, it mentioned the use of telecom parts. For example, just getting an insight of what commercial parts make the most sense to you. You know, what helps in the commercial space? What do you use in the commercial space? So it's very focused on the quantum memory, and it's wonderful. It's insightful. But what are those commercial parts that you're looking for?
Really good question. Actually, the quantum memory is probably the only part which isn't obviously commercially. That's something we make ourselves. So let's ignore that. But yeah, on that, you know, we're trying to move towards normal photonics telecoms components themselves. I think mostly, you know, in terms of the lasers that we use. So the process at the moment that we use to generate our single photons starts with, you know, telecoms laser systems. So 1550 sort of telecoms lasers, pulse lengths of sort of several hundred picoseconds. And then what we look to do is to sort of do a process of down conversion to down convert that. In fact, we do sort of a series of down conversions. So we down convert to sort of 780 and then down convert again to sort of 300 or 320. Mm-hmm. And then, you know, we then do a sort of 2 photon step to then bring us back to 780. So sort of throughout all those steps, that it then takes your telecoms laser system with many trillions of photons and turns it into one with just one photon. Okay. And so that's something. So obviously telecoms laser suppliers are important to us. So it's sort of somewhat bespoke. So the pulse lengths are quite long, but that sort of makes sense.
We have a lot of investors in the room. I also see Frank Levinson from Phoenix Venture. Hi, Frank. We have many people in the room that are really great today. I want to be a bit more specific here, Richard, because this is one key room for cooperation. One thing that you are not going to buy are going to be telecom products already available, but you have a problem you say in the beginning, my biggest problem is loss. I have a problem with the losses. If you could get the ideal telecom device with low loss, what would that be? We discussed about switches, we discussed about other components. Tell us about something and I'll try to find somebody in the room that can help you with that.
If I was going to name 2 things, so don't mind me saying 2 things. One is hollow core fiber filled with rubidium gas. This is like the holy grail for something that would, in terms of the memory technology we have, that would make a huge difference. So that's one thing. The second, probably more relevant to the general audience, is this idea for a very fast, low loss switch. So we're talking about something with sort of multiple 100 megahertz sort of switching speed, and then but combined at the same time with a loss of, well, our guys want a loss of less than 1 dB, but you know, we'll survive with something that's sort of not quite as good as that. Like, we're interested in what the art of the possible looks like. But
this is a clear room for cooperation with 3 people in the room, with Imec, with CSEM, and with AMO. The reason for this is, first, CSEM is developing a lithium niobate platform. Is that right, Amir?
Yes, it's a lithium niobate and insulator platform. We are developing. Do you want me to actually share a slide on this?
The slide is ready, of course. It's a clear room for cooperation here.
Sure.
Amir is looking for use cases for a new platform of silicon integrated photonics using thin layers of lithium niobate. And I'm super excited about this. I'm one of the fans of this technology. Yes, tell us.
Yeah, actually, this is a sort of a technology we've been developing for some years, and then we are trying to actually commercialize this in the form of a foundry. So the technology is based on a lithium niobate on insulator. I mean, lithium niobate is not a new material, but we use not a bulk lithium niobate, but rather thin films. And this allows us to do multiple function on the chips, taking advantage of the nonlinearities, the electro-optic coefficients. Just, lithium niobate has one of the highest electro-optic coefficients in the world. It's very fast. We can do very efficient and very fast modulation, switching at very low losses. So maybe managed to actually, bring losses below 0.2 dB per centimeter. One other advantage, which might be very interesting for quantum computing people, is that lithium niobate has a very broad transparency window. So it's transparent from 350 nanometer all the way to 5.5. So we can actually cover a lot of, bands on the same chip. And at the same time, we can actually use this nonlinearities to do multiple nonlinear effects, from down conversion, second harmonic generation, wavelength conversion, supercontinuum generation, together, mixed with this high, sort of transparency window as well as low losses. I think this could be a very interesting solution for, applications in quantum computing. And actually, we are already collaborating with some of the quantum computing people in the room, and I would be very happy to actually extend that if you're interested in this.
there is a lot of activities in Europe right now on actually enabling ultra-fast low-loss switches. So the lithium niobate is one platform. The platform that Imec is developing also, it's out of this world. The work that AMO is doing as well. I also introduced you to the people from TUI in Doven already for the indium phosphide platform. I want Europe to help Orca Computing. But I have another question for you. So we heard from Quandela. I know you know Quandela very, very well. You don't love them half as much as I do. Michael, if you could ask a question, you could ask a challenge for the single photon sources of Quandela. What would you like those sources to do for your platform? And dream away. And the sentence of Epic 2020 is, you are muted.
Yeah, good. I hope that helps. Well, so the challenge is twofold. One, the Quandela guy is going, our platform runs at 780 nanometers. So at the moment, their quantum dots are slightly different from that. So sort of if they can do a good job and sort of present us something at 780, that would help a lot. The thing with single photons is just this very complicated mixture of exactly one photon. So a G2 that isn't sort of mostly 2 photons, mostly 3 photons, mostly vacuum, but is most of the time 1 photon. And then indistinguishability, so very narrow bandwidth single photons, and then potentially the ability for multiple sources, for each of which can be indistinguishable with each other. So a good ability to interfere photons, single photons from different sources. So that's, I think the guys from Qandela know that already.
Yes, they do. But Valerian, challenge accepted, and that challenge, of course, is open for the Epic universe. Richard, thank you very much. Thank you so much, Nadia, for representing IBM here. We are going to come back to you, but now I would like to tell the investors in the room, now stay alert. The next one is one of the ones to watch. We go to the Netherlands and we go to my beloved company QuiX. We go to hear about the silicon nitride platform for quantum computing. Stay alert. This is really one of the ones to watch. Jörn, thank you all for being with us this afternoon. The floor and the attention of everyone goes to Enschede, goes to QuiX.
Thank you very much. Greetings from the snowy Enschede right now.
It's also snowing in Noordwijk, but the sun is also shining, so it's beautiful right now.
It is wonderful. So, thank you very much for introducing already QuiX. Yes, we are in Enschede, the Netherlands. I'm Jörn, project manager at QuiX. So, what is QuiX? We are a spin-off from the University of Twente, just 2 years old, and then founded by Hans van der Vleckert, which was, by the way, Epic CEO of the year last year, and Jelmer Renema. We're still located on the university campus and now grew up to a team of 9 highly skilled quantum engineers. So I think Richard already told a lot about the importance of photonic quantum computing also. So how do we see a quantum computer? It has basically 3 components, which is here the sources that go through interferometer and an array of detectors at the end. And what you would like to have is to have this all tunable. And we say, yeah, so that the photons build up via quantum interference, they build up entanglement, and you want to have this on a large scale. What we say, companies like Qandela already mentioned, have the sources available. The detectors are also available, but the platform in the middle, that's our core technology, to have a large scale, as large as possible, low loss, because you will need every single photon. And yeah, for that we use, as already mentioned, the silicon nitride platform. So, I mean, where do we stand now? What we now have available off the shelf is our 12-mode universal quantum photonic processor. It has here in total 12 input modes, so input waveguides, where we can send in single photons, by the way, right now at the wavelengths of 50-50, and also 12 interaction layers, which is the depth of the processor where the photons can interfere. Here, how does such a unit cell look like? It has a tunable Mersenne interferometer to steer the light, and also another phase shifter to control the phase. In total, it consists of 60 6 unit cell and has over 150 tunable elements. So yeah, it's all right now silicon nitride PIC technology. We can address in our control box every single thermal optic attenuator and have in our current generation low fiber loss interconnects of half a dB per facet, which leads up in our 12-mode processor to a high transmission of up to 60% with some minor difference between the modes, so that we end up with losses of 2.2 and 2.7 dB in total. So yeah, why do we need, why do you think that silicon nitride is the platform to go? This is also because it can be easily interfaced with common single photon sources. So we already talked about quantum dots. Quantum dots are now commercially available by Epping members. And yeah, indeed, we're currently working on implementing quantum dot sources within the focusing project, as Valerian already said, and to shift our wavelengths from to have 50-50 and also 930 to have the high quality sources available. But also 2 other members in this call already showed sources that are the parametric sources. So with Xanadu and Ligentec, a nice example of on-chip source, which would be, of course, very nice to get rid of the coupling losses. So how do we see that? So you can have our processor. It comes with a control box, which has all the it has control software where everything is already characterized, and you can easily swap the module and then dial your programs on our processor. So yes, our processor is completely reconfigurable, and our control software directly translates the voltage that is needed to dial your program into the phase you set, and takes care of all the other nasty effects that can happen. And finally, how good is what you do? How good is your programming? That is given by the fidelity, a figure out of merit of how close what you dial into your processor is to what you get. So let's start with an easy one of the to have a look at the processor working. So we have here the output modes against the input modes, and here we just switch through it, and we see that we already get a fidelity of 99% on normalized power. But you can also do some random permutations of the modes. So for phase independent, we average over 150 50 modes and have a fidelity of already 99%. So we pretty much have our processor under control. But you also want to have it phase dependent and can do arbitrary unitary transformations, matrix transformations with your processor, and also there we have almost 99% of fidelity of our processor. And you can also do some fun stuff. For example, we made the Q and the X of our logo, which is also you can precisely control what the processor does. And here also we averaged over 250 random unitary matrices, and we reach fidelities of 97%. But we're also interested in other custom solutions using silicon nitride technology with based on our expert team on quantum photonics. For example, this is an example of a silicon nitride chip that was used in ion traps, recently published in Nature. And this all built on the custom building blocks with, of course, other post-processing, but this is also something we are interested in and looking at. So, and we are also very open for strategic partnerships to develop use cases with our customers and to develop with them the next steps in the evolution of photonic quantum computing, and also, yeah, as said, custom-made devices are also possible with our knowledge we have in-house. So yeah, thank you very much. And if you have questions, just mail me or ask me now.
Thank you so much, Jörn. But you know how it goes with Epic meetings, right? You tell us what you can do, and we will ask you what can the others do for you. So when you want to go scale up your production, what are the challenges you see on the way?
Yeah, so one of the challenges we already talked about are sources, of course, and detectors. And then, of course, coupling losses to the PIC platform, which is already a high threshold. Yes, so many photons. We want to have as many photons as possible to put into our chip, and then we also are the wavelengths wouldn't really matter. So as long as it's transparent for silicon nitride, we are happy.
Yeah, please continue.
We are happy to collaborate there and such devices.
Yeah, that's very nice. I think it's really a nice time now to hear from Ligentec.
Hello.
Hi.
Yeah, great work, Jörn. What you showed, and you mentioned also what we can do is that we have this very high Q dispersion engineered resonators where you can directly generate the two photons on the chip with spontaneous 4-wave mixing. And that is possible because we have that very thick film silicon nitride that can be especially dispersion engineered, provides very low loss because you don't have any rough. Your mode sees very low, very less roughness, sidewall roughness, and you get a very small footprint and can do very compact resonators. And so Ligentec as a silicon nitride platform, this is one of the high Q resonators is one of the key components, but there is a whole bunch of couplers, AWGs, delay lines that all go with very low losses and very high power that you can propagate also in these waveguides. And obviously one key aspect is what you mentioned, and I think here we haven't reached the limit yet with 0.5 dB. I think we really all together need to go lower than that to have very good edge coupling and coupling from the fiber to the chip.
Thank you so much. And let me see also, we have from Imec. Amir?
Yes, thank you, Sana. I have also one slide.
Can you tell us how can Imec help QuiX here?
Yeah, so I hope you can see my slide also.
Yes, please go to, yeah.
Yeah, so at Imec also we have a photonic platform, but I wanted to also give a bit more broader than that. Actually, we are working both on the electronic way of quantum computing and also photonic. We have activity on superconductor and spin-based quantum computing, but also we have 3 platforms for the silicon and silicon nitride photonic-based platform for quantum, LPCVD, PCVD, and also we are merging this unique platform of silicon nitride with silicon photonics. So these are the platforms that are available in the also not only in the prototyping. We can manage it up to the volume of almost 1,000 wafer per year per customer. The unique thing about the Imec silicon nitride platform is that we have a process control almost nanometer over 200 millimeter wafer for the volume production. So we have this platform almost for 4 years as a product. This is extremely important, this thickness control of nanometer for the when you want to have a filter design, when you want to have a process on Mach-Zehnder design. So we are offering this platform for the different application. Quantum is one application. And in a nutshell, we are doing this in the 200 millimeter and also 300 millimeter platform, advanced lithography tools that we have. And we could just provide this, as I said, for the volume with the highest quality. Already some building blocks are available both on silicon photonic and also silicon nitride. We could even merge these two platforms together as a co-integrated platform. We already engaged in a couple of activity in quantum. For example, quantum key distribution with the Asian Academic Center and also some companies in North America. Thank you. Just I wanted to keep it short because I know that how it goes.
It's very important for us to hear what you do and see how we can do the collaboration. Let me see first if we have any questions in the room. Please, you can unmute and ask. Otherwise, I'm very happy.
I have a question because I love QuiX, and you need to ask this because otherwise people don't get it. So, you know, when it comes to this slide, which I just love, when it comes to the slide in which you show, and this is already proven in the lab, I have seen it. You have proven that you can actually do 12 optical mode computing. I call this computing, 12 optical mode computing. But we are talking today about qubits. Could you explain a bit the relation that you have between the optical modes that you're actually computing now and the future qubit computing?
Yeah, we always do not refer to qubits, but Q modes. So each photon in the input mode carries the information, and during entanglement by quantum interference, and afterwards measuring the output distribution, you'll get your computation. So, but maybe that's also a good question for for Xanadu, how that exactly translate to qubits. I would be interested.
One quick question from my side is actually I said that phase shift that you use, these are based on like a thermal,
Yes. Yes.
So are you not afraid of like basically thermal coupling between like the neighboring things when you scale up to too many basically components in the silicon nitride platform?
Yes, of course. But that's what we think we have under control by careful measurements and our control software, by just knowing our system very well.
But as you mentioned, the importance of the source here, I'm very happy that we have M Squared in the room. We have Thomas. Thank you for joining us today.
It's a pleasure.
Can you tell us a word about what you can offer?
Right, M Squared is a company based in Glasgow in Scotland and also one of the pioneers working in the quantum technology, rather in the quantum sensor side, so to say. However, we are also pioneering a few nice projects as well, also collaborating with a few big guys, tier one customers in that ecosystem, so to say. So we are claiming to offer the purest light source, so to say, necessary in order to provide the precise photon as a source, as an input later on a higher value chain then, so to say. So they're all based on a solid state laser platform, organized in tiny, nice little boxes. You can bundle like in a Tetris game, and you can collect, compile the photon source as requested with respect to the application.
Thank you so much for this nice summary of what M Squared does. But we have. Let me see first. Do we have other questions in the room? Because I think
well, Thomas, you've done a fantastic job with M Squared on bringing the laser into, as you say, a box. When it comes to the quantum sensors and the gravitometers, it is spectacular, the job of M Squared. So for any company that is looking for a partner to actually deploy gravitometers into any application, it is fascinating what you have done. But today it is a bit on the quantum computing side. Is there any room for cooperation? Because we want to help you. I love when a laser goes into a system, and I also know that you love that too. Is there any potential area to work together here?
Absolutely. As always, as usual, so to say, that's precisely what the folks in Glasgow are doing. There's a huge department based working on the innovation part of the company's business. Okay, I'm rather working with the sales end, so to say, but that's precisely the idea. As we all know, quantum is still quite early, so to say. It's a couple of years still out. The only way to success road is, of course, collaboration. Otherwise, we all know that currently we see a lot of huge fundings. We see a competition between the areas in the world globally. Yeah, it's nice. However, we also, with longer respect, look at my gray hair, I've made some experience. In order to avoid a quantum winter after the funding is gone, we need
quantum winter is not going to happen because Epic took charge. But you know, Thomas, it's about cooperation. So let me find you friends to cooperate. From DLR Quantum Technologies, Björn joined today the meeting. I want to hear from Björn a little bit what brought you to this meeting, what room for cooperation we could have with DLR, and what are you currently maybe working on? Björn.
Thanks for having the opportunity to be here. I'm a bit of a side entries to optical quantum technologies. I'm more coming from the superconducting side. But there are, of course, also people at DLR working. I mean, if I hear about gravitometry, there are certainly people working there. So for me, I just want to get an overview of what is going on in this field and get some ideas and yeah.
You are an expert on the microwave quantum optics, and I had to say that one of the reasons that we wanted you to be here, we do have companies in the microwave photonics generation, and it is something that we see as a room for cooperation. So offline, I think you really should get in touch with the people that you just spoke, especially the guys from Ligentec, that I think there is perhaps some nice room for cooperation. Thank you very much, Björn. Sana, what do you say? Do we go to the next speaker? Let's do that. Let's go to the next speaker. Let's go to the beautiful, beautiful, beautiful city of Aachen. I really can't wait to start traveling again so I can go to visit them. From Fraunhofer ILT, Bernd Youngblood is with us to tell us how we can make Fraunhofer ILT in quantum greater than it already even is. The floor and attention of everyone goes to Aachen, goes to you.
Yeah, thank you for this really nice introduction. Can you see my screen already?
Not yet, not yet.
Not yet. So then
go to the bottom of the room and put share screen.
Okay, I think I got it. So now?
It's almost here. Yes, it's perfect. The floor is yours.
Perfect. Thank you. So again, thank you very much for the nice introduction and the opportunity here to introduce our Fraunhofer Institute for Laser Technology here in Aachen, and especially our contributions to the field of quantum technology. Now it doesn't work as always. I want to skip to the next slide.
Use the spacebar.
Spacebar also doesn't work.
Okay, so
actually it should work. It's not the first time I tried it, but
the spacebar should work.
Okay, somehow I think so. For the next speaker who has the same trouble, the right mouse click helped. So perhaps it's the same for you. So hurry up. So I think here in this optical community, Fraunhofer ILT is for sure better known for its contributions in the field of development of high power lasers, industrial laser processing, or in the nowadays very rugged optical systems and lasers which go to the satellite for LiDAR applications. But as you see on this slide, we also have some significant first projects in the field of quantum technology. And here we see that we can contribute on different levels. This starts with space technology like lasers and optics, but also in integration of some simple or even advanced optical systems for example, can you see the pointer here? Here, if I move it, otherwise
we can see the pointer very well.
Okay, I will try. So now there's a laser here. As in Fraunhofer ILT. Yeah. Okay. So for fields like quantum metrology, communication, and quantum computing. And here on this outer circle, you can see the different projects we are working in, and they are also listed here on the left-hand side. And during these projects, we realized that one really important thing at the moment is really to push the ecosystem you have around with industry involved, and therefore with the research partners here in the region, for example, the other Fraunhofer institutes in North Rhine-Westphalia or the research center in Jülich, we really try to push an initiative on a center of quantum science and engineering to really give the region and the industry here in the region a big push and start business cases here around. So, but beside these future plans, as we have to call it now, there are also running projects, and one of the most interesting ones that we have that which is in the center of the presentation now. This is in close cooperation with our partners and QuTech, which have the aim to install something like a quantum internet. You may have heard of these ambitious plans they have. They heading to demonstrate an entanglement distribution network based on fibers in 2022. And we are allowed to bring a little part inside this. We are collaborating in the field of photonic components you need for such a quantum internet. And the speciality we have in this first phase is what we call a quantum frequency converter. And now let me go a little bit into the technical detail. So what is a quantum frequency converter? So plainly speaking, this is a black box which does nothing else but converting an input photon at, for example, 678 nanometer to an output photon at 1587 nanometers, so in the telecom band. While this input photon is entangled with some stationary qubit, here in our case it's an NV center, the conversion setup does nothing else but changing the wavelengths and keeps all the other properties of the photon as they are, and then we keep also the entanglement, and due to low losses in optical fibers, we can distribute the entanglement on NV centers over large distances. If we have a look inside the box, we see there is no Schrödinger cat inside, but mature laser technology. So we have a high power laser, a nonlinear frequency converter, which is driven by it. And of course, a lot of spectral filtering to separate one single photon in the output band from all these laser power that we have. So in the project, we are following two different approaches. So one is what we call the baseline approach for the QFC at QuTech. That is the working horse in the project. So because this is already developed on a high level with proven performance, and this works on a piplin waveguide. So due to the high nonlinearity of the lithium niobate compared with the spatial confinement in the waveguide, we see also for this single photon input a high conversion efficiency, and even the noise is already on a quite acceptable level for scientific experiments. On the other hand, so the noise that we have, let me go back. No, just keep it. Due to the noise that is expected through inhomogeneities here of the polling or roughness of the waveguide, we expect that this can be limiting in the end if we go to really high volume applications of this technology. And therefore, we at Fraunhofer ILT, we explore an alternative scheme, which we call NORA, which stands for Noise Reduction Approach. And here we do not have any polling or no waveguides on the cost that we use a simple KDA waveguide, KDA crystal, bulk crystal, and to ensure high efficiency, we put this into an enhancement cavity. So if we compare both schemes, then we see directly this right-hand side scheme seems to be more complex. And an engineering question is if we can get it as rugged as the other solution that is here shown on the left-hand side. But due to our experience with OPOs and lasers which go on satellites, we are quite optimistic that we have the technology, the mounting technology for such a solution at house, if we can solve the more scientific problem at this point, which is, can we have an acceptable efficiency, and is this approach less noisy than the other one? And actually, we are not as far as I can give you really fully characterized data, but I can say we are quite far in the lab. So we have a running system, and we also made some first conversion experiments, at least with classical sources, very low input power. And at the moment, we are working with comparably low intracavity power here in this regime. And yeah, we have already seen conversion efficiency now in the range of 30%, as our simulations had already predicted. And we see that there is still room to increase the intracavity power, so that we are quite optimistic. And additionally, some first of our experiments indicated that the noise level could be as low as we expected. So there's a lot of optimism at the moment. We are on track, and I think the next time, or in a really good publication, we will show more on this, what we have now. The plan currently is to go to QuTech as soon as we can in springtime, perhaps, if Corona allows us, and then we will make hopefully some first experiments with the colleagues over there and compare the two approaches. So thank you for giving me a chance to talk, and you're welcome to ask questions now.
Thank you very much, Bernd. As soon as you go to QuTech, QuTech is in Delft. It's very close to where I am. So please stop by and let's have dinner. I really, really can't wait to start traveling again, Bernd.
Yeah, great.
This is an epic meeting. Yeah, an epic meeting is about cooperation. And I love cooperation. You know that. Is there anything that you think the rest of the epic members can do for you apart from QuTech and that you can do for them?
Yeah, sure. Let me answer this on two different levels. So the very simple level is what you see here. So we can, of course, cooperate with components and materials, because the clue or the performance of our converter significantly depends on how good the quality of the optical components inside is. So we need low losses, high quality materials, which can withstand high power. So that's the simple answer on what we could need from outside. But the second level of answer is we are a research institute, and we are looking for partnerships with people from photonic industry. And as mentioned before, I think for them it's still a long way to go to a technology where no large market can be directly addressed now. So by all the optimistic statistics that we have, what will happen in 5 or 10 years for SME partners, it's hard to give the money and the effort into this topic now. And therefore, we are looking also for people which are optimistic and which want to go with us into this area and inspect where they can roll out their technology platforms and look where they have their specific advantages in quantum technology.
Bernd, this is clear, no, but I want to do cooperation. So you say that you say low losses and high power. I am at all, believe me, I am at all not worried about the losses. I know it sounds crazy, but I'm not worried about the losses. I'm a bit worried about the power. How much power do you need?
Input power we have at the moment at this 1064 nanometer about 5 to 10 watts. So that's moderate, but they have to be with a narrow line width in the kilohertz regime. So we need narrow band lasers.
Narrow band lasers is okay, but 5 to 10 watts. Let me look at the different platforms that we have today. We have VLC Photonics in the room, right? From Valencia, my beloved VLC Photonics, Hitachi VLC Photonics. Giovanni, he's looking for a platform, a photonic integrated circuit platform that we can input 5 to 10 watts, and it doesn't really burn.
Yeah, there is a nice question. Yes, we can use photonic integrated circuits that can provide very high robustness to high power, like for example, silicon nitride. It can be one example of our friends in Ligentec.
Let's go there. Let's go there. Michael from Ligentec. How much power can you put inside your silicon nitride chip?
The most we did is 10 watts, and
there you go.
And we didn't have the EDFA to put higher power, so that's
okay.
And pulsed. If you put pulsed wave, you can go up to peak powers of kilowatts. So that's
So we're in business here, Bernd. Furthermore, there is a question for you coming all the way from beautiful Switzerland in Neuchâtel. What's on your mind?
Yeah, hi Ben, this is a lovely presentation you had. I loved it. Actually, I have a question on your TPLN efficiency. So can you describe it, instead of input output per watt, what is the conversion efficiency per watt?
Actually, the first question is, what power level do you mean? The intercavity power that is enhanced, or the really power that we give into the cavity?
Well, if you compare the non-resonance one, we'll answer the other one as well, because we can just enhance it by finesse. And
yeah. Okay. So then one would say we took the output power. So the outer power, the laser power that we give in. So in the case of the QuTech, the baseline approach, this is some 100 milliwatts, and of course we have a lot of more input power. But one has to have in mind that this power is not really wasted by the conversion, so it can be reused afterwards.
Sure. But so it's a 17% per 100 milliwatts. Is that what I understood correctly?
So sorry, I cannot really hear you. So
17% per 100 milliwatts, or 70% per watt, sort of a efficiency that you're getting right now, right?
Yeah, it seems feasible. So I haven't calculated it before. So, but yeah, you see all the values you have here, and yeah.
There's of course a separate discussion that you want to have. Once again, I want to say, Bernd, that we want to have use cases for the platform that we are developing with lithium niobate in CSEM, and this is of course a clear use case. So we have to have a separate discussion on that. But I want to keep finding you partners, Bernd, and I'm going to find you a partner in the UK, my beloved UK, part of the beautiful continent of Europe. I want to go to Cambridge Consultant. Edmund, thank you very much for being with us. I love your hairstyle, and I also love the technology of Cambridge Consultants. Is there any, from what you heard today, what do you do? What are you working on in quantum, and what room for cooperation do you see here?
Hi, thanks very much, Jose. Yes, so Cambridge Consultants, we're a group of 900 engineers, scientists, and designers. We work on systems integration. So we've 60 years worth of experience creating products, developing new products for ambitious clients. So yeah, so we offer engineering services to make that happen. In quantum, really interested in finding out about this new technology. So we're always trying to keep on the edge of what there is, and quantum definitely fits that bill for us. So yeah, I think in terms of what everyone can do for us, we're really looking to see which of these technologies we can integrate into the things that we make. So it's all cutting edge stuff. So really interesting to hear from all of the speakers and from all of this.
Cambridge Consultants have been instrumental with many of our members actually developing instruments for the medical sector. On this, they really truly excel. And of course, we are going to hear a few cooperations on biosensing between Epping members and Cambridge Consultants. I don't know if I'm spoiling anything, but in the coming months. And it's being really clear for me that you have some room to play also in the quantum technologies. Thanks a lot, Edmund. I can't wait to go there and drink a pint with you. I want to continue with the potential cooperations, and for that I need to move to a next speaker. Before that, I want to go to one of the key companies that we have as a platform, as a one-stop shop from design to manufacturing iterative photonics. I want to go to PhotonPath. And the reason why I want to go to PhotonPath is because we heard a lot of opportunities for you to contribute, right? Douglas, what's on your mind?
That's right, Jose. Thank you a lot for the kind intro. Yes, I've been hearing quite a lot of possible nice collaborations that we can make, and for that, let me present myself. I'm Douglas. I'm the CEO for PhotonPath. We are a spin-off from Politecnico di Milano, here in Milan, in Italy. And we are photonic designers, manufacturers, and assemblers. So we have a spin-off that was founded in 2019. And maybe I can share one slide that I have here so things can be a bit clearer to all of you. We, as I've mentioned, we are based here in Milan, and our main, let's say, our vision is that as pretty in line with everyone is talking here, it is that light it's the perfect instrument to obtain, to transmit, and to measure, and to process the world's information, right? And we are backed by VCs here in Milan. And let me just jump into what we can offer. We are mainly a one-stop shop that from which you can jump to us for design services. You know, virtually all the integrated photonics platforms. We have experience in designs for silicon nitride, silicon oxynitride, silicon by itself, indium phosphide. We provide also prototyping and testing services, and we also have our own components for telecom applications at this moment. So what we in a single slide, if I can show you what we have been doing, what we are up to, is to help people to go through all of this complex cycle of the photonic integration, from the choice of the proper platform for your specific application to the design of the components, to the testing, and passing through packaging into the control of these devices. So if you have anything that comes into mind when it regards about photonic integration, you can definitely reach to us here in Italy.
I have a thing that comes into mind direct away. So we are looking for ultra low loss, and we are looking for certain high power level. What can you do on that topic? And is there perhaps some ideas for cooperation on that?
Definitely, as Michael mentioned from Ligentec, we also have some collaborations with Ligentec. We have tested some of their chips, so we have experience in the designs for their platform. So if you need any specific support in helping for design for their platform, we can do it. I also have just met Amir from CSEM, where you can also help you guys to use all of these capabilities that these founders have to offer.
But do you have any idea on how to actually design the entry point, the waveguide, to actually incouple 10 watts? And can it be purely single mode, or what kind of structure do you have in mind?
We have some. We also have some custom designs in our partner foundries here in Italy, from which we have designed papers that provide very, very low coupling losses, very, very low birefringency, very, very low propagation losses. So all the optical design for such components, we can also help you to understand which design is better suited for your specific application. So anything that comes in mind, we are here.
Bern from Fraunhofer ILT, I told you I'm going to find you partnerships. Many partnerships I'm going to find you. But the next one is Sony. Faisal, what's on your mind?
Oh, sorry, I was mute. Yeah, I was just wondering about the services. So you're a white label company, I suppose, that you take the design, you produce the design, and then transfer the IP to the customer? We
are a one-stop shop, so it depends on a customer basis. So some customers approach to us to design their own products. So yes, so we provide the whole IP, and we also have some our custom products for our own from our own devices, mainly for telecom market, for amplifiers, mini ROADMs, and so on.
So yeah, that's what I want to understand. Are you a pure play company, or do you actually have your own product and which can become a competition to your potential customers as well?
No, our customers are mainly in telecom. So for telecom, yes, for telecom specifically, we have our own products. So that's the kind of customers that we are. That's our own market. Let's call it like this. But for markets like quantum, like sensing, we can definitely be of support to do custom developments, understand requirements, and design their own solutions.
Douglas, you have you push this market, like you came and you disrupt with your concept of having the whole value chain together at one point. You actually have based this into the beautiful story, beautiful success story of VLC Photonics. And I have a beautiful comment from Intelligent. Oh my God, Valerie is here. I can't wait to start traveling again and see my friends. When I see you, I get so happy. You are muted. What's on your mind? Yeah, we have you muted. It's a sentence of Epic 2020. You are muted, yeah. Valerie. Yes.
Thank you, Jose. So I'm mute because I cannot say too much about quantum computing. I'm not in this area by any means, but you know what? The farther we go, the more I hear about this component, that component, and the impression is that this is not the last thing the community needs. Sufficient and tailored to the needs components, which will provide whatever functionality you're looking for. So if anyone is interested, we do some custom development, peaks or standalone devices of this nature, lasers, detectors, combined modulators, passive optics with them, and that's what I think about looking at this as a cooperation.
Thank you very much, Valerie. You have made a few success stories in your life, quite many actually, and this one that you are doing now with the indium phosphide integrated photonics manufacturing.
It's phosphide, so lasers and detectors are yours.
And the cooperation that you're doing with VLC Photonics is out of this world. But I want to go back to you again. But before that, there is part of the story that we didn't talk yet, which is the instruments to make the whole thing working and testing. And for that, we have an amazing Epping member, Keysight, Mark Almendros. Thank you very much for being with us today, Mark. The floor and the attention of everyone goes to the most amazing company when it comes to testing equipment, goes to Keysight. The floor is yours.
Oh, thank you very much. Thank you very much for the nice introduction. Let me share the screen. Can you see the screen?
Crystal clear.
Okay, perfect. So yeah, I'm going to talk about what we do in Keysight for Quantum. I'm the technical director of what we call the Quantum Engineering Solutions Group. And I'm going to present basically solutions for control and also for test and measurement in general. So as you know, well, just a quick introduction. As you know, we started as HP, right? So the first products in HP were test and measurement products. Test and measurement division then was split then into Agilent in the 1990s and then into Keysight, right? So over all these years, since we were HP, we have helped to our customers to really enable the innovation, right? And innovation, of course, in all those 75 years, innovation in many different fields, and quantum is certainly one of them, right? If we look at our portfolio, what I'm going to show today is control systems for quantum computing, quantum communications and sensing, so in general to control qubits, and also some traditional test and measurement solutions focused on the optic ones, right? Because you know already that we have scopes, spectrum analyzers, all the typical test and measurement equipment. So let me talk about control systems. So what we offer are basically, well, two types of control system. One, which are modular control systems, which are designed for highly scalable applications in which you need, for example, to control many qubits. But we also have a wideband control systems. Like, for example, we have AWGs up to 256 gigasamples per second. So if you want to generate very short pulses, for example, you can do this with those AWGs. But let me focus a little bit on the modular ones, which are the ones designed, of course, for quantum computing. And so we provide this a full control stack, which is basically composed of software and hardware. And basically starting with the hardware, what we provide are AWGs, digitizers, microwave LOs, and so on a modular form factor. In this case, in PXI, is highly scalable. You can really control hundreds or, well, in fact, you can control an unlimited number of qubits as long as you have enough room and budget. And here I put an example of a trap ion experiment or a trap ion quantum computer. It could be also for communications or for sensing. We also have customers in superconducting qubits, spin qubits, and so on. But for this meeting, I keep it in trap ions. So you can generate any kind of RF pulse to modulate lasers. You can generate microwave pulses. You can generate baseband pulses to control shutting electrodes, for example. You can read out through digitizers single photons. And the key part of the hardware is also all the associated software that we have. And we have basically three key technologies. One is the open FPGA capabilities, so that you can put really custom digital signal processing and on the AWGs, on the digitizers, so you can do custom detection algorithms, you can do a custom pulse generation in real time. And this allows you to do fast feedback and to do things like quantum error correction or qubit reset or any kind of feedback algorithm. And all this, of course, is handled by a real-time sequencer, which also provides a real-time synchronization between all the modules. And in addition to this, we provide higher stack software components, like, for example, like Ladder, which is a recent acquisition, in order to do, for example, experiments in a very easy way and in a very comprehensive way. We provide this kind of control system not only for R&D, which of course many customers buy to build R&D demonstrators, but we also have customers that use them for commercial quantum computers, right? Because in that way, we allow our customers really to focus on their core business, which is the scientific part, right? Solving the quantum problems by leveraging really all our electronic experience. And then if we go to the classical test and measurement equipment, apart from the classical ones like scopes, spectrum analyzers, and so on, we also have a portfolio of photonic test solutions, right? And this is very relevant for communications, of course, but also is becoming extremely relevant for quantum, especially in all the devices that work at telecom wavelengths, right? So we provide optical sources, we provide the signal analysis like wavelength meters, we provide optoelectronics S parameters measurement, so you can measure S parameters at the optical wavelength, polarization analyzers, stabilizers, synthesizers, and in general a wide range of components like power sensors, optical heads, attenuator switches, and so on. So this is an example of a swept wavelength measurement platform together with the application software, and this is and we can really deliver very complex test and measurement solutions. Like for example, this is a wafer and die probing solution that we do because we have partnership with probe station manufacturers like FormFactor or Cascade, for example, and together with our equipment, really we provide really very comprehensive solution for both for the electronic side, but also for the optical side. And that's all. Thank you very much.
Thank you so much, Mark, for this great presentation. Let me see first if we have. Let me ask you first the epic question. Yeah. Now you show us what you can do, and we want to know what can the others do for you. What is the next technology that you're trying to work with, and what collaboration can we find for you?
So yeah, it's basically all about collaborations, right? What we can do for our customers is to provide them the value of all our electronic expertise, digital signal processing expertise, software expertise, and so that they can focus really on their core business, right? That's the main thing, because in order to advance in quantum, I think there needs to be a strong collaboration between engineering and the physics and the scientific side, right? So that's the first thing. This is what we can do. And in terms of collaborations, we are open for any collaboration, right? We want to hear all the challenges you have, right? And how we can push the test equipment really to overcome those challenges, right? So basically bottlenecks, right? Things like you say, okay, I would like to test this thing in a much faster way. I would like to reduce my testing cycles in order to speed up my R&D and to shorten time to market, right? This is our expertise and where we can collaborate.
Yeah, this is really nice to hear, and I work with myself when I was doing research with your instruments, so I totally understand the value of that in the quantum field. So I would like to also introduce another Epic member that are having a great wafer technology for quantum applied for quantum technologies, IQE. Ivan, how do you find the meeting so far, and can you tell us what you do?
Yes, thank you very much, Anna. Yeah, of course. Yeah, IQE's been a member of Epic for a very long time now, and you know, we've been instrumental in providing epi wafers, commercial epi wafers to the community for over 30 years now. And just to pick up on some terminology that we heard earlier, I think it came from Faisal. I think that Sony, we are a one-stop shop, and we are a pure play epi wafer manufacturer. I do have a couple of slides, by the way.
Yeah, please share.
Helps,
you can share with us a slide that we understand better how you're going towards the.
So, are you able to see that?
Yeah. That's
okay. So
presentation mode.
Just to say, yeah, we are a pure play epitaxy provider. We have 10 sites globally, but we are headquartered in Cardiff here in the UK. And at the bottom left, we see our new mega epi wafer foundry in Newport. Across this region where I am in the UK, we have 24 MOVP tools with in-house characterization. And just so to just to make it clear, we are a one-stop shop for epitaxy, which basically covers photonics, wireless applications. So as far as quantum's concerned,
would you mind going to my full presentation mode, please?
Of course, yes. Thanks for reminding me. Yeah, I just wanted to give one example. So, I think it was Thomas up at M Squared Lasers. They're in Scotland, we're in Wales, and we're part of the big UK quantum technology community. And there's been substantial investment in this in quantum technologies for roughly 6 or 7 years now, and we have some very big national programs. So I just wanted to point out that what IQE's role in quantum technologies is simply to produce epi wafers, which provide for single photon detectors and emitters in the material systems we can see up there, and also VCSELs. We have VCSELs for atomic clocks, magnetometers, but certainly the largest applications will be in quantum communications, computing, imaging, and sensing. One example of a national quantum technology program is called QFoundry. I think we have a meeting in April 23rd, I think, Jose. And I think I'll be providing a little bit more information than I am today, but I just give you a snippet of news there from Electronic News, EE News Europe, and some quotations. We have a great consortium here of UK companies who are involved with making single photon sources, quantum dots, single photon detectors, VCSELs, for all sorts of quantum applications. And the rationale behind this project is that we want to put together a technology platform to make these devices and these components more robust, reliable, and reproducible. So that's it from me for now. Thank you very much for the opportunity. Any questions?
Thank you so much. Thank you for joining us. And yes, we will hear from you on the 23rd on our the number 6 of our series of quantum technology meetings. And now, just to stay in the spirit of the one-stop shop, we have one of our very nice Epic members, VLC Photonics.
Hi.
Guillaume.
Yeah, so thanks for the introduction. I just have a quick slide here to share with you.
Yeah, sure.
Let me see.
So we will hear about integrated circuit again, so photonic integrated circuit from you.
Yeah. So as you mentioned, we are a one-stop shop. We are a photonic circuit design house.
Can you go into a presentation mode?
Sorry. Sure.
Yeah. Just to see it bigger.
It's here. Yeah. So we are a design house for photonic integrated circuits. So we are based in Valencia in Spain, and this year is a important year for us because we complete 10 years of existence. We have about a team of 17 people with a lot of experience in the academic and industrial world. As you mentioned, that we are a one-stop shop, so we provide engineering services since the system concept to the device design, circuit design, and layout. So we outsource. We are a fabless design house, so we outsource the PIC fabrication, and then we get the wafers and the dies to test in-house. So we have capabilities of chip and the wafer testing, and some capabilities of packaging low volume. We work in many fields of applications, of course, including quantum photonics. We have some clients on this field. Also, of course, other applications typical for integrated circuits like telecom, sensing, LiDAR, and so on. We also participate in many projects, R&D projects, and also some pilot line projects. For example, Impulse, which is a indium phosphide pilot line project, in which the objective is to develop a manufacturing grade PDK and process, INP process, in order to facilitate the development of new products in several application fields, of course, including also quantum computing. So if you have interest to bring your products to a photonic integrated circuit, if you are in a prototype level or pilot line level, you can contact me and then we'll discuss with more details. Thanks.
Thank you so much for this nice summary. And I bet everybody is waiting to hear the quantum computing side from Xanadu, right, Giesz? Thank you for joining us. Can you just give me at least a comment or your impression about the meeting so far? And do you see already some collaborations?
Yeah, absolutely. It's great to be here. It's great to be in this epic meeting. So many nice talks and nice results and possibilities of nice collaborations. Thanks so much.
All right. So we're looking forward to hear about your talk. You can just start.
Perfect. Okay. Yeah, so as I said, it's my pleasure to be here at Epic, at this Epic meeting. It is not my pleasure to be standing between you and your weekend. So let's get right to it. Yeah, so I want to talk about the work that we are doing at Xanadu, which is a photonic quantum computing company. We are building a scalable photonic quantum computer. And when I say scalable, so I mean the full thing. I mean a full fault-tolerant quantum computer with millions of qubits, physical, and hundreds of logical qubits. This is the device that will enable those magical applications that, for example, Richard mentioned, and also unlock this $1 trillion market. And yeah, so there's a $1 trillion market, which means that the race to build a fault-tolerant quantum computer is on. I want to highlight that this race is a marathon. So this slide is famously from Google. It's about superconducting qubit, but it's really representative of many different platforms. So on the x-axis, we have the number of qubits. More is better. On the y-axis, we have the error rate. Of course, smaller error is better. And right now, we're somewhere here with tens of qubits and 1 part in 100 error. But we need to be in this green region of useful error-corrected quantum computing. And as you can see, we are 5 to 6 orders of magnitude away total in terms of the number of qubits and the error rate. So if you're really far away from where you need to be, the thing that matters most is scalability. And as far as scalability is concerned, photonics, and in particular Xanadu's approach, is really unmatched. And this is because we have an architecture. I'll get into more details of this architecture on the next slide. But I want to mention some salient features of this. So first is that photonics allows you to have a modular quantum computer. So basically you have many modules or chips which are identical to each other that are then interconnected, networked. And the cool thing about photonics is that networking comes for free because the networking is also done optically. Our computer, because of the particular choice of qubits and because of the architecture, it operates at room temperature. And of course, this has advantages in the sense that it's easier to build because all the electronics that are required to do the computing, all the electronics required for the error correction, this is very fast, high power electronics. All of this can be at room temperature. And also, it allows us to iterate much faster because we don't need to wait for a cryostat to warm up and then cool it back down to the temperature of outer space in order to just change a chip. And with photonics, the extra advantage is that we can manufacture our chips with very little modification to existing CMOS processes. This is not the case with superconducting qubits, for example, where the kind of materials that you have to deposit are just not compatible with the leading foundries. Okay, let's dive a little bit deeper into this architecture now. This is from a blueprint that we recently put out. You should be able to find this online. And you should think of this slide as giving a flavor of what we are building, and also to some extent an answer to the epic question of how we can collaborate. So let's get right to it. This 3D structure is our resource state. This is what allows us to perform computation. The dots here are qubits. There was a question about qubits, Xanadu's qubits earlier. And yeah, so for us, the qubits are either squeezed states of light or states that are constructed using squeezed states of light. So these are the so-called GKP qubits. And as Richard mentioned, yeah, the qubits that we have some amount of loss tolerance built into the qubits themselves. And how is this resource state generated? Well, we have the state factory. This is the part where we generate either the squeeze states or these so-called GKP states. And the state factory requires nonlinear optics integrated and photon number resolving detectors. For these detectors, we're working closely with NIST at Boulder. And this part has to be really low loss because here is where the interference is happening. But once we have the qubits, the next step is to multiplex them together. So you can spatially multiplex many different qubit sources. And this allows you to boost the rates, so the speed of the computer, but also boost the probability of getting these qubits. And as you can imagine, this part has to have fast optical switching. But because of the qubits that we are using, we don't need super low losses. And then these qubits are stitched together on the so-called computational module. This is, I would say, the most benign part of the architecture. So only linear optics, this I think is super scalable. Once the cluster is created, the computation is performed on this QPU, on the quantum processing unit, which comprises a whole bunch of homodyne detections. And for that, of course, we need photodiodes that are operating at room temperature on the chip, along with local oscillators, which are basically so coherent laser pulses running on the chip. Yeah, so these are the different parts of the architecture. Happy to talk more about it in the questions or offline. And with that, I want to say that we are very we are very actively hiring researchers and engineers on quantum computing, on photonics and analog electronics. So yeah, come work with us. And thank you for your attention.
Thank you very much for this. It is actually the second time that you are invited to an Epping meeting, and after your first presentation, I made, I think, 8 different introductions to different companies who could help you with some challenges, and you presented them, and you followed up with many of them, and people gave me really good feedback about this. So thank you very much for making Epic even epicer. But Giesz, let's see about what we can do with this community. So can you give me just one challenge, and I will find you a partner. Give me a Santa Claus Christmas list of 1 or 2 items maximum.
Perfect. Yeah, I should say that these are also things that we are working on, but definitely open to collaborations. So the one challenge which is most pressing is the generation of these qubits. And for that, we need nonlinear optics, hopefully integrated with low loss. So I guess there were all these discussions already about nonlinearities that can be on integrated photonic platforms. So this is definitely one challenge that we are looking to address very soon.
Nonlinear optics integrated. Be prepared, Giesz. There's going to be a lot of cooperation starting from this statement. But we have Faisal has something on his mind from Sony. Faisal, what's on your mind?
Thanks for the introduction, Giesz. I was just wondering about the structure that you showed. Is it a real 3D structure, or the operations on the qubits are done on a planar level only? And the second adjacent part was essentially, which you kind of alluded to as well, what's the efficiency that you achieve in the generation of these qubits?
Okay, so I'll address the second question first. So what's the efficiency that we have in the generation of these qubits? Yeah, these qubits are generated non-deterministically. For a single device, for a single small 3-mode or 4-mode device, you can generate these qubits with a probability of something like 1%. Then if you put hundreds of these small devices together, and since they are such small devices, you can put many of them together, you can boost it to whatever probabilities you like. So this is not a problem. Could you repeat your first question, please? I lost track of this.
That was on the structure part. So it seemed like a 3D structure, but the operations of the qubits themselves, are they planar actually, or do you actually in real life conduct a 3D operation, which is going to be a different domain then?
100%. That's a great question. And yeah, so it is a 3D structure, but it's 3D in the sense of space, time. So Richard also mentioned that you can do stuff in the time domain with optics. So yeah. 2 of our dimensions are planar on chip. The third one is in the form of time. So everything is manufacturable with normal chip. So integrated photonics does the job.
Thank you very much, Giesz. The second question comes from my friend Jeff from the main one. Jeff, what's on your mind?
Oh, yes, thank you. You had mentioned you're looking for, fast switching time. Can you give any insight into what fast is?
Yeah, absolutely. So through different generations of our computer, there will be different requirements of fast. Initially, we are looking at megahertz speed computers, which is still, I think, quite fast. So the multiplexer would have to work at megahertz speeds. But eventually, since we are talking about photonics, these computers can be really fast. So eventually, we would want to go to tens of megahertz or even hundreds of megahertz.
Thank you.
Thank you. Quick question from my side. What sort of insertion losses do you actually, can you also comment on that? Because I think this is crucially important for you guys.
Yeah, I think there are different parts of the architecture. And so most of the parts are very tolerant to losses because we have these loss tolerant qubits. The part where losses need to be brought down more, and we are working very hard on this, this is the part of the state sources. So you need losses below 1 dB or so. So from the source till the detector.
Thank you very much. I think I have a potential cooperation here. You know, in Epping, we have all the different types of companies. And in Epping, we have ST Microelectronics. From what I have seen so far from most of the technology we presented today, and we'll make a summary in a second, it is clear to me that what we need is an integration platform for these technologies to be integrated. And especially when it comes to the detectors, integrated detectors, ST Microelectronics is the only company we have in Epping that will make this happen. I have no doubt. But we have you represented here. What's on your mind, and what perhaps got room for cooperation have you spotted after these 2 hours?
Hey, hello. So very nice meeting and very interesting presentation. I was really happy to join this meeting so far. So the topic of quantum detectors is really key, and indeed I think this is one of the real research challenges that are still ongoing, because so far all the solutions I know they are not compatible with CMOS. So we need to find something that is CMOS compatible. So I guess from our point of view, yes, this is a real challenge so far. And we did not started to work on that. We are working on the sources, on the hybrid 3.5 silicon sources for photon generation and toggle photon generation, but we did not start yet to tackle with the detector problem. That is, I guess, still a huge research problem.
It is, and I do fully agree with you that we need to find a way that is either CMOS compatible or hybridly integrated in a very high volume suitable fashion. And this is for me the next big thing in quantum, to have the technology that can allow us to have single photon detection to some extent. And everybody's gonna say, no, we have single photon with the fantastic coolers, by the way, single photon you're watching, hello. But we need to go into something more manufacturable. And in the coming months, we will address this particular topic. Before I say goodbye, I cannot say goodbye without acknowledging the presence here of people in the micro-optics domain. For example, Ruth from ThinkMade, also multi-photon optics. Ruth, how are you today? We have heard a lot about integration. We have heard a lot about integration with virtually low losses. And for that, there is nothing better than customized optics or micro-optics fabrication. Is there anything you can do in this business?
Yeah, hey, Jose, hi all. Yes, I think people at Multiphoton might do something about the micro-optics. So as you all see, I'm in the transition rate somehow. So we'll be leaving soon, and I'm very looking much forward to continue working in this micro-optics and optical integration sphere. So I'm pretty sure that Multiphoton can actually do a lot in this type of business, particularly with respect to the fact that this company was actually built by the vision that we would like to revolutionize computing systems by doing interconnects and connecting the devices. So,
Ruth, you've driven the customized micro-optics manufacturing, making equipment suitable to volume production and being able to make them as small, even to have nanometer resolution. Ruth, you are never going to be gone. Ruth, you and me, we are in this business for as long as we are alive. I'm sorry.
Gone.
I want to go now to my friend. I'm going to shoot in the air. Frank Levinson from Phoenix Venture Partners. Frank, thank you so much for being with us today. We are almost at the end of the meeting. I couldn't close the meeting without giving you the word. What makes you excited about the photonics industry entering the quantum technologies market?
For sure that it doesn't require cold temperature.
all the things that we have, there's a lot of infrastructure that supports it. One connection I wanted to make for several of you with Richard at Orca and others is a group called Nexus out of UCSB, I can't pronounce his last name. They have ways of putting down thousands of devices on silicon nitride to build an active substrate. And I can't really say more, but I think for all of you that are looking to do integration, I would start there.
Frank, I fully agree with you. I think in this business, it is clear that we have already mastered the low losses. And the next step is really the integration of active components, because these people in the quantum business, they can't afford any kind of the use of any photon. And this is what I see. I'm going to summarize here what I have learned in these fantastic 2 hours. The first thing is that we look at 2 different technologies. We look at PICs and we look at fiber optics. So QuiX, Xanadu, and Ipronics told us a bit about the integrated photonics for quantum, while in the fiber optics, Orca Computing told us about their dream. I think in the integrated photonics, it's clear we have an advantage. This is that companies like Ligentec, Imec, they have really mastered the low loss. They have mastered with the silicon nitride platform, they have mastered the low loss. We have the challenge into inputting some high power, and also the challenge into having also active components integrated. The low loss for quantum are there. On the Orca Computing said, I'm going to take a different path. I'm going to try to take off-the-shelf components. What happened? The biggest challenge is low loss. That's their biggest challenge and the bigger room for cooperation. Any company that can actually manufacture any telecom device with ultra low losses, Orca Computing wants to talk to you. And there were some common challenges for everyone. We talk about single photon sources. We talk about the detectors. For a single photon source, we want the efficiency, and Quandela has mastered that in the single photon detectors. It was very clear from ST Microelectronics. The next step is to integration in semicon process, and for that we need new materials and we need CMOS compatibility. This was the first online quantum technology meeting. What we wanted today is to bring the technologies that we already know. So we were in our comfort zone. We talk about fiber optics and integrated photonics. I was super comfortable today. I want you to make me uncomfortable. On the next meetings on quantum technologies, when we address the defense sector, when we address the medical sector, it is about learning new technologies that photonics can enable. That will be the next step. Do not miss the meeting on defense technologies. If you want to participate on the online quantum technology meeting on defense, send me an email and I will make sure you get the secret link. Of course, for obvious reasons, the online quantum technology meeting on defense will not be on YouTube. So if you are expecting to have a passive role and learn everything, do not do that, because it will be a secret meeting. On behalf of a fantastic team of experts from the European Photonic Industry Consortium, almost 700 companies supporting us, I would like to say thank you for making a quantum boy and Sana, a quantum girl, happy. This is the calendar for the upcoming online technology meetings. Register if you see anything that is relevant for you. And in the meantime, wear a mask, wash your hands, and live long and prosper. Take care. Bye-bye.